everyone. So we're very happy to have Peter Koltai from the FU Berlin. He's going to talk about the birth and death of coherence, semi-material coherent sets.
Great, thank you very much. Thank you for having me. So, as many others before me, I'm grateful to the organizers for putting this together, for the invitation. It's really lovely. So, yes, this is a joint work with Gary Freie from the UNSW. It's on the birth and death of coherence, and I should tell you what do I mean with this. So many have been considering the evolution of fields, climate models, atmospheric models. Before me, this talk is going to be assuming that I have a time-dependent velocity field given for some time, and I'm going to be interested in actually Lagrangian evolution, so transport in the flow, which is driven by these given velocity fields. I would, in order to understand something about transport here, I would like to find structures which are most robust under transport. They are least mixing under a small diffusion on top of the Lagrangian evolution. So think of this cartoon as having two sets. There is some diffeomorphic action, so some flow of a non-autonomous field from this time s mapping to time t, and you see what happens to the black set and the gray set. Now, if we apply just a slight amount of diffusion, either continuous in time by an STE or instantaneous, which are sampled by these red points, you see what happens. The black set contains most of its diffuse points, while the gray sort of doesn't. And to make this effect a little bit more dramatic, let me pull back the whole situation, the whole picture, by the deterministic evolution, which was here, right? So this is the inverse of the flow, and you see the red diffuse points of the gray set are dispersed all over the place. So this is how we see what a diffusive, slight diffusion on top of the Lagrangian evolution does. So this is the idea, what led to the concept of finite time coherent sets, pioneered by Gary Freie and co-workers, and this is where we are going to elaborate on. The setting I'm working with is that I have a fixed time interval for simplicity 0 tau that is given, and I'm given also a velocity field on this. So I don't know more about the velocity field. There is no tau going to infinity or so. For simplicity, I assume that it's always divergence free, see incompressibility everywhere. I assume that most of the theory can be extended to the non-divergence free situation, but at a cost of a lot more technicalities. There is also a set of interest of initial conditions that is called M. So for simplicity, it's connected, compact, and so on, somewhere in RD, and representing my state space initial conditions, right, at t equal to 0. So the flow map from t equal to 0 to sometime t is going to be encoded by phi t is just a solution of this non-autonomous orientation. So this is setting the stage. And now what I'm interested in is how a small perturbation introduces mixing in my deterministic system. So this was my ODE. I'm adding some noise. For simplicity, epsilon is just some small scalar. I'm looking at the Kolmogorov forward equation. So that means from this SDE, I'm going over to densities. UT is the distribution of my random XT, and this is the Fokker-Planck-Kolmogorov forward equation, which if you probably know. But what I'm interested in is how this noise is spreading material, is mixing on top of my Lagrangian evolution. So I'm pulling everything back with my flow here, with my deterministic flow. Yeah, think about the previous slide where I was pulling back the red points. And what I realized is that I also have a Fokker-Planck equation for this situation now. Obviously, or perhaps not obviously, but intuitively, the advection term is vanishing because I pulled back by the deterministic advection. But the price I have to pay is that my diffusion operator, my Laplace operator, is now going to be twisted and is encoding the effect of the dynamics. So I just write Laplace T. It has some specific form, which I will comment on just in a minute. But next step I would like to see is what happens if I do some kind of a epsilon asymptotic expansion of the situation, right? I'm thinking of epsilon being small. So epsilon 0 would mean that I'm kind of implementing the identity, right? I'm going forward with my Fokker-Planck equation, then I'm pulling back, but everything is deterministic, so this part isn't here. So U tilde, my pullback evolution, has U0 in zeroth order term. And now, if epsilon is something positive, the combination, the joint effect of diffusion and dynamics is switched on. And this is what we get. It's an averaged, twisted Laplacian. So the integrand is what I call the Laplace T here, or delta T. It's a push forward, diffusion, pullback kind of combination. And I have to integrate it from 0 to tau to get the net effect. And everything else is of higher order terms. So this operator, both the integrand and the integral, are going to play a central role in the following. Right, now to the movies. So how does this operator tell me anything about mixing? For the sake of visual intuition, I will show you two movies. Think of material stuff which I'm mixing being added positive and negative sign. Right? I have positive and negative mass somewhere in my flow field, and it's going to be red and blue here. If I let the flow evolve, advection plus some diffusion, positive and negative stuff is going to hit one another and cancel out. And that is going to be purple in my movie. But in this sense, I'm going to kill mass in my system through this cancellation. So as this cancellation occurs, the total norm, L1 or L2 norm of my signed distribution is going to decrease. This decrease is going to be captured by the operator I showed you before. So I'm starting in the same flow, I'm injecting this blue and red ink at different points. And you see on the left-hand side, I see quite a bit of purple quite soon, while in the right-hand side, I seem to have injected the ink in proper places such that not much mixture is happening. And the question is exactly, how do I find the right-hand side situation? So yeah, if I look at the very end, and I stop it, you see there is a lot of purple there, a lot of mixing happening, meaning the associated sign function is having a small norm, and I'm missing a line here due to visualization effects, but the main issue is that my main point here is that eigenfunctions of this operator tell me how signed distributions look like, which decay slowly. So think of the right-hand side movie, which unfortunately you cannot see here, and that will kind of pinpoint coherent sets. So the message I wanted to go away with this slide is that eigenfunctions of this operator and their positive and negative parts tell me where I can find coherent sets, which are slowly decaying under diffusion. Test.
not working anymore? All right, I'll try to just speak up. All right, put the back factor. Says red, code red.
Did you try moving closer to the
To the mic?
yes.
All right. Coherence can be also quantified in this situation, and it's governed by the associated eigenvalue. Okay. However, nothing lasts forever, right? I have to find the right time window, 0 tau, in order to be able to carry out the previous analysis in terms of, if the window is too long, it's not guaranteed that there is at least any coherent set which is consistently coherent for the whole time. Also, if the time window is too short, then there is no mixing which can happen. So there is no coherent set which emerges from its mixing environment. If we think of coherent sets, for instance, eddies, vortices, at least in the ocean, they have typical lifetimes. They form, they exist, and eventually they decay. What we would like to know or find is a characterization of how to find the birth and death of coherent sets together with where they are. And this hasn't been done so far. That's the new part. Trial and error is obviously a possibility. Try different time windows in the velocity field which you have given, but that's just too costly. And we want to go beyond that. Okay. So we have to relax materiality. Materiality was this Lagrangianity that I'm starting with a set and I'm following its Lagrangian evolution with respect to the flow all the time. I have to resolve time somehow. So I'm going to time expand my state space, and that will lead me to a time expanded domain M0, which is just taking my initial conditions and slice-wise putting it together. So basically topological, I'm having 0 tau. This is the time interval times m. Physically, it's perhaps better to think about a co-evolved manifold where at every time I'm looking at a flown forward manifold, but all these two situations, or both these situations, are equivalent to one another. It will be just better to think in terms of M0, M0, which is the left-hand side of this picture. So if I have M, it's just a strip, there is some coherent set in it. If this coherent set lives from the beginning to the end of my time interval, time is the horizontal axis, then I see a picture like this. In a co-evolved frame, this sausage would be the coherent set. What I'm interested in is rather this situation where coherent sets can start to live and die at some point. And I would like to find these times. Now the construction we are going to look at on this space-time manifold is the following. Recall that there were these Laplace T's which were describing how diffusion acts in conjunction with the Lagrangian evolution at time t, if we put it back to the initial conditions. And now on every time fiber, t times m, I have this operator acting. But now I have to connect the different time fibers. And for reasons, unfortunately, I don't have time to tell you, the right way, or a natural way, is to connect them via diffusion in time. So we introduced artificial diffusion in the time component with some strength A, which we are able to tune. Now, this box has a lot more information than I just said. There is also a differential geometric view on the whole situation, connecting coherence to the isoperimetric problem. You know, in case you care. In case you don't care or don't know what I'm talking about, just think of this operator, which can be understood and used completely without differential geometry. But otherwise, we have a metric tensor, and the Laplace Beltrami operator with respect to that is what we are looking at. All right. Getting these, so forgetting differential geometry again, we are going to solve this spectral problem, this eigenvalue problem, and we are searching for space-time eigenfunctions f of this operator. We have Neumann boundary condition in time phases. We realize that this problem has some kind of skew product structure. You know, the time t influences this diffusion operator, but there is some pure time component which allows the problem to have some purely temporal eigenfunctions, which are nothing else than different cosines of this sort. We call them temporal eigenfunctions. We can extract them, we throw them away. We don't want to have them. Everything else is going to be spatial, and because of the self-adjointness of the operator, it's going to be also that spatial eigenfunctions are orthogonal to temporal ones. So we extract these spatial eigenfunctions, and now we compare them to what I've been telling you before, to the so-called dynamic Laplacian, which is nothing else than the average of all these delta t diffusive ones. Am I doing on time? 5 more minutes should be, right? So the dynamic Laplace operator was designed to find coherent sets which prevail for the whole interval of time, 0 tau. Okay. We now have something where we suppose, I haven't shown you any pictures or justification so far, but it's going to lead to coherence on some sub-interval of 0 tau. Think of the eigenvalues of the dynamic Laplacian, lambda 1, lambda 2, and so on, with the d as a superscript. They were describing how coherent sets decay, how much do they mix during the whole time interval. We are going to compare them to eigenvalues, spatial eigenvalues, or eigenvalues of spatial eigenfunctions of our new construction, and is a theorem associated to it. So if we order eigenvalues of the dynamic Laplace operator and spatial eigenvalues of our inflated dynamic operator, then we have this. Then we have this equality. These are negative numbers. The closer we are to 0, the less decay a coherent set experiences. So this tells us that if we do a time-augmented setup, we are able to find functions, hence sets, through their sign structure, which these guys experience less mixing than sets which are frozen in time, meaning they are material. What happens if we vary A? If we tune up spatial diffusion, then we are going to decrease eigenvalues, meaning temporal diffusion. More temporal diffusion leads to less coherence. Temporal eigenvalues go to -infinity as A goes to infinity. As A goes to infinity, spatial eigenvalues converge to dynamic Laplace operator, which is perhaps not surprising if we go back. If I tune A to infinity, I'm somehow making these functions, the eigenfunctions, more rigid in the temporal direction, right? I'm enforcing constancy in a way, and eigenfunctions which are constant in time are kind of the eigenfunctions of the averaged operator. There's a little bit more math to it, but that is basically the gist. So this parameter A interpolates between completely non-material situation, right? A equal to 0, I have no connection between different times, and a fully material setting where the connection is as strong as possible, so there is constancy of eigenfunctions in time. Thing is, we have to find the right A to find really the timing of coherent sets. So last but not least, here's an example of a so-called Chedrosard flow on a 2 torus. So it's called cat's eye flow because there's a parameter in the string function. So here you see streamlines. Trajectories are parallel to the lines you see here. If this parameter r is 0, then we have 4 vortices. If it's 1 or -1, you see shear, right? Shear like this or shear like this. And what we are going to do is in our time interval, in the first 25% of time, r is going to be 0. Perfectly nice coherence, 4 coherent sets, you know, just nice gyres. And then we start to switch back and forth between +1 and -1 of r. So we are going to kind of alternate shearing this in this direction, hence we introduce mixing. What we would like to find is where these coherent sets are and see when mixing hits in. So if we solve the problem, this eigenfunction problem, with some a, which we find with a heuristic I'm not discussing here, on actually an unstructured grid of well, approximately 1,000 trajectories, and we see the spectrum, which we can classify to temporal and spatial modes. Throw away the temporal ones, keep the spatial ones, which are the dots. We see there is a group of 3 and then some gaps. So in the very first, which is also a spatial mode, we expect 4 coherent sets to be there. If you look at the picture, we were happy, because there are also 4 coherent sets, and these are slice-wise L2 norms of eigenfunctions in time. So this is the time interval, and this is now the eigenfunction, these 3 here, and they're slice-wise L2 norms. So you see when mixing hits in, this is where the dashed line is put in, that's where basically we decay to 0. So we have a nice, actually this is a cosine or cosine squared profile, which we can extract or use to extract the timing of these coherent sets. Sorry. And if I'm looking at different times the values of the eigenfunctions, these are spatial eigenfunctions, row by row, then I see that their sign structure will tell me where the coherent sets are located. And also, as time evolves, when mixing hits in, that's the middle column, I'm already seeing a little bit of decay of norm, and a little bit past that point, the norm of the eigenfunction is already small enough. So, you know, just alluding to this picture, from these plots, we are able to diagnose when coherence has ended and when mixing starts. This is just a more dramatic way of showing the same picture. This is time, and whenever values converge to 0, you know, they turn white. So you see how trajectories have large values along eigenfunctions, and you see how when mixing hits in, we lose norm and we find timing. This is a multiple coherent regime situation. So there's coherence until the first dashed line, then there's mixing again, then coherence, and then mixing again. And you see the different eigenfunctions. These are, again, the L2 slice-wise norms, pick up different coherence sets, different regimes. Obviously, we would like to go beyond our nice cat's eye flow and do something relevant in atmospheric or ocean sciences. This is just some preliminary data on a polar vortex, preliminary results on a polar vortex data set. In 2002 or 2003, there was a splitting in the polar vortex data. In the polar. It's over Antarctica, I should say, and there was a split in the polar vortex, which we are picking up here. So kind of you see this this figure 8 structure which is happening. This is time. We are looking at a 2-dimensional surface. Obviously, realizing that I should have told you way more about what am I actually doing here, but you know, just preliminary everything. This is if we try to find coherent sets on the whole interval of time. You see that because of this spinning off, I get some filamentation, E spot. So somehow this is not perfect coherence. if I'm employing our new method, we see that it rather kills the coherent set at some point and reforms a new one, which can be seen as some part of this coherent set actually spinning off. It's not coherent anymore. It dies as a coherent set and a new one arises. Summing up things, I showed you how we are extending the material coherence situation to a non-material coherent set setting by a characterization, and also we developed a tool to find not just where coherent sets are, but simultaneously also when they exist. And just want to briefly mention that it is a very nice triangle of different theories coming together. There is an SD part, there's an operator-based part. Those two I was trying to show at least a little bit in my talk, and I was alluding to that there are connections to nice things in geometry. Yeah, it's a parametric problem. Right, advertisement. I will be moving to the University of Bayreuth, and there will be a postdoc position. I would be grateful if you could inform interested candidates who are somewhere on the interface of data science and dynamics to contact me. And with this, I would like to just flash this slide. This is the paper we were talking about. There are some more if you're interested in the evolution of this field and these ideas. And many thanks for your kind attention.
Okay, so we have time for a couple of questions.
Yes, very nice new set of ideas. You know, can you go back to the beginning of the slide when you actually introduced the operator, the dynamic Laplacian, one involving the integral. Yes,
This guy.
is good. So in practice, we will have to estimate the push forward and the pullback effect.
Mm-hmm.
And so, okay, for the flows that are given analytically, this is not a big deal. For like now, if I have like, you know, if I think about like a passive tracer or like, you know, like real fluid situation, so I would need like to have like a lot of these points,
yeah,
like to be flown one way and the other way, right?
Mm-hmm.
And I'm sure you have like thought about that. And so I would just like to know like how robust is the eigenfunction to let's say the number of points that are required. I mean, in other words, what do you have an estimate on the number of points that are required to be flown, right, in a push forward and a pull back? Get like robust estimate of this eigenfunction.
Right. So the way you approximate the operator is not necessarily through the formula which I have shown you. I was trying to get to my numeric slide, which somehow doesn't work. Oh, maybe now. So we do have a method for unstructured trajectory data, which trajectory data means they are, you know, flown forward. We get trajectories at certain time points, and there is a possibility from there to approximately infer those operators which we require to set up the problem without the need to think about how to compute push forwards and pullbacks. So basically, take your trajectory data, mesh up time to time, so each time with triangulation, and do some very simple computation. You have an approximation. How well that works?
But you will need several trajectories, we agree.
Pardon?
You will need still several trajectories.
Obviously, from 3 trajectories, I'm not able to say anything about mixing, right?
Yes.
So that's completely fine. Well, what was the resolution here? 30 by 30. I think on this example I've shown you with the pet map where I have 0 to pi times 0 to pi, so torus, 20 by 20 trajectories are completely fine, maybe even less. And then it really depends on how the temporal and the spatial resolutions play together. I really do need to see the effect of mixing in my finite amount of trajectories. You know, if that's not there, I don't expect any reasonable results to be seen.
And in 3D, it can be, of course, extended, the approach.
Obviously, yes.
Well, I can see for, oh, sorry, I thought you were moving. I can see how you do that in the ocean because you have a lot of floats.
Yes.
But how exactly do you do it in the polar vortex?
Well, what we are doing is there's some data on the velocity field. We have it at grid points, so it's probably output of a model, maybe somehow assimilated, and the Freie analysis might be. We interpolate between the grid points and put the floaters where we want them to be and simulate.
I think that's one last question.
In order to understand in more real cases you've shown whether you get coherence or not, I think you need to think of active scalars rather than pre-prescribed velocity field, like thinking of saying about the potential vorticity, for instance, is an active scalar which will influence the velocity field as well. I think you won't really get anywhere with understanding when you get coherence or not without doing that.
Sorry, that was already a question.
That was sort of, well, that was if you like,
Sounded like a
I see how you
comment.
react to that. I think you're missing a key part, a lot of fundamental elements of trying to understand why you say get breakdown of coherence in other vortex or an or something like that.
The way we were setting up things, it was really for advective plus small diffusive transport with respect to velocity fields with particular properties.
Yeah.
We have been looking at, for instance, temperature fields and asking about heat coherence. There are ways to bridge this theory over there. It's not as rigorous as I've shown you there, but if you're interested, we can talk a little bit afterwards. It's been a Rayleigh-Banach convection where we were looking at this situation and finding something of sort of heat coherent sets. So that goes, I suppose, in the direction of your question, right?
When we talk about
All right, let's thank Peter once again.